Electrical and electronics engineering interviews test technical knowledge, problem-solving skills, and practical applications. 1. What is the difference between a conductor and an insulator? A conductor allows electric current to flow easily due to free electrons, like metals, e.g., copper. An insulator resists current flow, having tightly bound electrons, like rubber or glass. Conductors have low resistance, enabling efficient energy transfer in wires or circuits. Insulators have high resistance, preventing unwanted current leakage, ensuring safety in cables or devices. Semiconductors, like silicon, fall between, with controlled conductivity. In electronics, conductors form circuit paths, while insulators protect against short circuits. For example, copper wires conduct electricity in a motor, while plastic insulation prevents shocks. Understanding material properties is key in designing efficient, safe electrical systems. Conductivity depends on electron mobility, temperature, and material structure. This distinction is fundamental in applications like power transmission, circuit design, and safety systems, ensuring optimal performance and reliability in electrical and electronic devices. 2. Explain Ohm's law and its practical applications. Ohm's law states that voltage, V, equals current, I, times resistance, R, expressed as V equals IR. It governs the relationship between voltage, current, and resistance in a circuit. Practically, it's used to design and analyze circuits. For instance, in a resistor circuit, known two parameters allows calculation of the third. Engineers use it to select appropriate resistors for LEDs to prevent burnout or to size wires for safe current flow in power systems. It's critical in troubleshooting, like identifying faulty components by measuring unexpected voltage drops. In power distribution, Ohm's law ensures efficient energy transfer by minimizing resistive losses. Limitations include nonlinear devices like diodes, where it doesn't apply directly. Understanding Ohm's law is essential for circuit design, ensuring components operate within safe limits, and optimizing performance in applications like amplifiers, motors, and renewable energy systems. 3. What is the function of a capacitor in a circuit? A capacitor stores electrical energy in an electric field, created by two conductive plates separated by a dielectric. It blocks DC while allowing AC, making it vital in filtering, timing, and energy storage applications. In power supplies, capacitors smooth rectified voltage, reducing ripple. In signal processing, they filter high-frequency noise, ensuring clean signals in audio or communication systems. Capacitors also enable phase shifts in AC circuits, critical for motor startup or oscillators. Their capacitance, measured in farads, determines energy storage capacity. For example, in a timing circuit, capacitors control oscillation frequency with resistors. They're also used in coupling amplifiers, passing AC signals while blocking DC bias. Proper selection of capacitance and dielectric material ensures circuit efficiency and reliability. Capacitors are indispensable in electronics, from smartphones to power grids, for stabilizing, filtering, and timing functions. 4. How does a transformer work? A transformer transfers electrical energy between circuits using electromagnetic induction. It consists of two coils, primary and secondary, wound on a magnetic core. When AC voltage is applied to the primary coil, it creates a varying magnetic field, inducing voltage in the secondary coil. The voltage ratio depends on the turns ratio between coils. Step-up transformers increase voltage, while step-down reduce it, crucial for power distribution. For example, high-voltage transmission reduces energy loss, and step-down transformers supply safe voltages to homes. Transformers operate only with AC, as DC doesn't produce a changing magnetic field. Efficiency is high, but losses occur due to core hysteresis and copper resistance. They're used in power supplies, chargers, and grid systems. Understanding turns ratio and core material selection is key to designing efficient transformers for specific voltage and power requirements in electrical systems. 5. What is the role of a diode in electronics? A diode allows current to flow in one direction, acting as a one-way valve in circuits. It's essential for rectification, converting AC to DC in power supplies like in phone chargers. Diodes protect circuits by preventing reverse current, safeguarding sensitive components like microchips. Zener diodes regulate voltage by allowing reverse current at a specific breakdown voltage, used in voltage stabilizers. Light-emitting diodes, LEDs, convert electrical energy into light, widely used in displays and lighting. Schottky diodes with low forward voltage are ideal for high-speed switching in computers. Diodes also demodulate signals in communication circuits, extracting information from radio waves. Their operation relies on the p-n junction, where doping creates directional conductivity. Selecting diodes based on forward voltage, current rating, and speed is critical for circuit reliability and efficiency in applications from solar inverters to automotive electronics. 6. What is the difference between AC and DC? Alternating current, AC, periodically reverses direction, while direct current, DC, flows in one direction. AC, typically sinusoidal, is used in power grids due to efficient transmission over long distances using transformers. DC is common in batteries, electronics, and solar panels. AC's voltage can be easily stepped up or down, reducing power loss in transmission lines. DC provides stable voltage, ideal for sensitive electronics like computers. For example, household appliances use AC, while smartphones rely on DC from rectified AC or batteries. AC is generated by alternators, DC by batteries or rectifiers. Conversion between them uses rectifiers, AC to DC, or inverters, DC to AC. Understanding their differences is crucial for designing power systems, ensuring compatibility, and optimizing energy efficiency in applications like renewable energy, electric vehicles, and consumer electronics. 7. Explain the working of a transistor. A transistor, a semiconductor device, amplifies or switches electrical signals. It has three terminals: emitter, base, and collector, in BJTs, or source, gate, and drain, in MOSFETs. In a BJT, a small base current controls a larger collector-emitter current, enabling amplification. For example, in audio amplifiers, transistors boost weak signals for speakers. In switching, transistors act as on-off switches in digital circuits, like microprocessors. MOSFETs use voltage at the gate to control current, ideal for high-speed switching in power supplies. Transistors operate based on doping and charge carrier movement in semiconductor materials like silicon. Their ability to amplify or switch makes them the backbone of modern electronics, from computers to communication systems. Proper biasing and selection, e.g., NPN, PNP, or MOSFET type, ensure optimal performance, efficiency, and reliability in circuit design and applications. 8. What is a microcontroller and its applications? A microcontroller is a compact integrated circuit with a processor, memory, and input-output peripherals, designed for embedded systems. It executes programmed instructions to control devices. Microcontrollers are used in automotive systems, e.g., engine control units, home appliances, e.g., microwave timers, and IoT devices, e.g., smart thermostats. For instance, in a washing machine, a microcontroller manages motor speed, water levels, and timers based on sensor inputs. In robotics, it processes sensor data to control movements. They're programmed using languages like C or Python, with platforms like Arduino or PIC. Their low power, small size, and versatility make them ideal for real-time applications. Key features include analog to digital converters and communication interfaces like I2C. Selecting a microcontroller depends on processing power, memory, and I/O requirements, ensuring efficient control and automation in consumer electronics, medical devices, and industrial systems. 9. What is the purpose of a relay in circuits? A relay is an electromechanical switch that uses an electromagnet to control a high-power circuit with a low-power signal. When energized, the coil creates a magnetic field, closing or opening contacts to control current flow. Relays isolate control and load circuits, enhancing safety. For example, in home automation, a 5 volts microcontroller signal can activate a relay to switch a 220 volts appliance. They're used in motor control, lighting systems, and automotive circuits, e.g., car starters. Solid-state relays offer faster switching without mechanical wear. Relays provide high current handling, electrical isolation, and compatibility with different voltage levels. Their design ensures reliability in harsh environments, like industrial automation. Selecting a relay involves considering coil voltage, contact rating, and switching speed to match circuit requirements, ensuring safe and efficient operation in applications from HVAC systems to power distribution. 10. How does a feedback system work in control systems? A feedback system monitors a system's output and adjusts its input to maintain desired performance. In a closed-loop system, sensors measure output, e.g., temperature in a thermostat, and the controller compares it to a set point. The error difference drives corrective action via actuators. For example, in a motor speed control system, a tachometer feeds back speed data, and the controller adjusts voltage to maintain constant speed. Negative feedback reduces error, ensuring stability, while positive feedback amplifies it, used in oscillators. Feedback improves accuracy, reduces disturbances, and enhances system reliability. Proportional integral derivative, PID, controllers are common, tuning response for precision. Applications include robotics, HVAC, and autopilots. Designing feedback systems requires analyzing stability, gain, and response time to avoid oscillations or delays, ensuring optimal performance in industrial automation, aerospace, and consumer electronics. 11. What is the significance of power factor in AC systems? Power factor measures the efficiency of power usage in AC systems, defined as the ratio of real power, kW, to apparent power, kVA. A low power factor indicates reactive power, reducing efficiency and increasing energy costs. For example, inductive loads like motors cause phase shifts, lowering the power factor. Capacitors are used to correct it, aligning voltage and current phases. A high power factor, close to 1, optimizes energy transfer, reducing losses in power distribution. Utilities penalize low power factors as they strain grids. In industrial settings, improving power factor lowers electricity bills and enhances equipment lifespan. Engineers analyze power factor using meters and design correction circuits for efficiency. Understanding power factor is crucial for designing cost-effective, reliable power systems in applications like factories, data centers, and renewable energy installations, ensuring minimal waste and optimal performance. 12. Explain the operation of an operational amplifier. An operational amplifier, op-amp, is a high-gain voltage amplifier with differential inputs and a single output. It amplifies the difference between the inverting and non-inverting inputs. In a closed-loop configuration, feedback resistors set gain, enabling applications like amplifiers, filters, and oscillators. For example, in an inverting amplifier, input signals are amplified with phase inversion, used in audio systems. Op-amps are ideal for precision tasks due to high input impedance and low output impedance. In integrators, they process analog signals for control systems, while in comparators, they compare voltages for decision-making in digital circuits. Op-amps require dual power supplies for linear operation and are sensitive to noise, requiring careful design. Their versatility makes them essential in signal processing, medical devices, and instrumentation, with selection based on bandwidth, slew rate, and power requirements for efficient circuit performance. 13. What is the role of a fuse in electrical safety? A fuse is a safety device that protects circuits by breaking the connection when current exceeds a safe limit. It contains a metal wire that melts under excessive current, interrupting the circuit to prevent damage or fire. For example, in household wiring, a fuse protects appliances from short circuits or overloads. Fuses are rated for specific currents, ensuring they blow before equipment damage occurs. They're simple, reliable, and cost-effective, used in automotive, industrial, and consumer electronics. Unlike circuit breakers, fuses are single-use and must be replaced after blowing. Proper fuse selection, based on current rating and response time, ensures safety without frequent tripping. Fuses complement other protections like surge suppressors, enhancing system reliability. Understanding fuse characteristics is critical for designing safe electrical systems, preventing hazards in applications from power supplies to heavy machinery, ensuring compliance with safety standards. 14. What are the types of electric motors and their uses? Electric motors convert electrical energy into mechanical work, with types including DC, AC induction, synchronous, and stepper motors. DC motors with precise speed control are used in electric vehicles and robotics. AC induction motors, robust and low maintenance, power industrial machinery like pumps and fans. Synchronous motors with constant speed are ideal for compressors and generators. Stepper motors, offering precise positioning, are used in 3D printers and CNC machines. Brushless DC motors, efficient and durable, are common in drones and computers. Each motor type suits specific applications based on torque, speed, and control requirements. For example, induction motors dominate HVAC systems due to reliability, while stepper motors excel in automation. Selecting a motor involves analyzing power supply, load, and efficiency, ensuring optimal performance in applications from household appliances to renewable energy systems and industrial automation. 15. How does a solar cell generate electricity? A solar cell converts sunlight into electricity using the photovoltaic effect. Made of semiconductor materials like silicon, it has a p-n junction where light photons excite electrons, creating a voltage. When connected to a circuit, this generates current. For example, in solar panels, multiple cells produce usable power for homes or grids. Efficiency depends on material quality, sunlight intensity, and cell design. Monocrystalline cells offer higher efficiency, while polycrystalline cells are cost-effective. Solar cells operate silently, with no moving parts, making them reliable for remote power systems. They're used in calculators, satellites, and large-scale solar farms. Challenges include low efficiency, 15–20%, and dependence on sunlight. Innovations like perovskite cells aim to improve performance. Understanding doping, band gap, and cell structure is key to optimizing solar energy systems for sustainable, clean power generation in diverse applications. 16. What is the purpose of a grounding system? A grounding system connects electrical circuits to the earth, ensuring safety and stability. It provides a low-resistance path for fault currents, preventing shocks and equipment damage. For example, in homes, grounding protects users from faulty appliances by directing excess current to the ground. It stabilizes voltage levels in power systems, reducing interference in sensitive electronics. Grounding also mitigates lightning-induced surges, protecting buildings and devices. Types include equipment grounding, for safety, and system grounding, for stability. Proper grounding requires low-impedance connections and regular testing. In industrial settings, grounding prevents static buildup in hazardous environments. Engineers design grounding systems based on soil resistivity, fault current, and equipment type, ensuring compliance with safety standards like IEEE. Effective grounding enhances reliability in applications from power grids to medical devices, minimizing risks and ensuring operational safety. 17. Explain the concept of Kirchhoff's laws. Kirchhoff's laws analyze electrical circuits. Kirchhoff's current law, KCL, states that the sum of currents entering a node equals the sum leaving it, ensuring charge conservation. Kirchhoff's voltage law, KVL, states that the sum of voltage drops around a closed loop equals the supplied voltage, reflecting energy conservation. For example, in a series circuit, KVL calculates voltage distribution across resistors. In parallel circuits, KCL determines current splits. These laws are fundamental for circuit analysis, used in designing amplifiers, power supplies, and communication systems. They apply to both AC and DC circuits, though AC requires phase considerations. Engineers use them with tools like nodal or mesh analysis to solve complex circuits. Understanding Kirchhoff's laws ensures accurate circuit design, troubleshooting, and optimization, enabling reliable performance in applications from consumer electronics to industrial automation and renewable energy systems. 18. What is the difference between analog and digital signals? Analog signals are continuous, varying smoothly over time, like sound waves, while digital signals are discrete, represented by binary values, zeros and ones. Analog signals, used in traditional radios, are susceptible to noise, degrading quality. Digital signals, used in computers, are robust, allowing error correction for reliable transmission. For example, analog audio fluctuates in voltage, while digital audio encodes sound as bits. Analog circuits process natural signals, while digital circuits handle data in microprocessors. Conversion between them uses ADCS, analog to digital, and DACS, digital to analog, critical in smartphones and TVs. Digital signals enable faster processing and storage, dominating modern electronics. Analog signals suit applications like sensors, where continuous data is needed. Understanding their differences guides circuit design, ensuring compatibility and performance in communication, audio, and control systems, balancing precision and noise immunity. 19. How does a battery store and release energy? A battery stores energy chemically and releases it as electrical energy. It consists of an anode, cathode, and electrolyte. During discharge, chemical reactions at the anode release electrons, flowing through an external circuit to the cathode, generating current. For example, in a lithium-ion battery, lithium ions move through the electrolyte, while electrons power devices like smartphones. Charging reverses this, storing energy by driving ions back to the anode. Battery capacity, measured in ampere hours, depends on electrode materials and design. Types like lead-acid suit vehicles, while lithium-ion powers electronics due to high energy density. Efficiency and lifespan depend on charge cycles and temperature. Understanding electrochemical principles ensures optimal battery selection for applications from grid storage to electric vehicles, balancing energy density, cost, and safety for reliable power delivery in diverse systems. 20. What is the role of a power inverter in renewable energy systems? A power inverter converts DC from renewable sources like solar panels or batteries into AC for grid or appliance use. It uses switching circuits, e.g., MOSFETs, to create sinusoidal AC output. For example, in solar systems, inverters enable household appliances to use DC-generated power. Types include grid-tied, off-grid, and hybrid inverters, each suited for specific applications. Inverters also synchronize with grid frequency and voltage, ensuring seamless integration. Advanced inverters provide maximum power point tracking, MPPT, to optimize solar panel efficiency. They include safety features like anti-islanding to protect grid workers. Efficiency, typically 95 to 98%, impacts system performance. Selecting an inverter involves matching power ratings, efficiency, and grid requirements. Inverters are critical for renewable energy adoption, enabling clean power in homes, businesses, and microgrids, supporting sustainability and energy independence in modern power systems. These 20 questions and answers cover essential electrical and electronics engineering concepts, equipping candidates with concise, practical knowledge. Mastering these ensures confidence in interviews, showcasing expertise in circuits, systems, and emerging technologies for career success.